Okay. Just wait for a few minutes and then start. In the meantime, if you guys have any questions, feel free to ask. Okay, let's start. Before that, I'll recap whatever we covered last week. So, first of all, is the const casting, right? So, we take a variable integer I, okay, and let's say we set it as 10. So, we can now create two data structures in a way, you can say, from it. So, one is the pointer and one is the reference. And this is the reference. So, first of all, the pointer, we define it to point to the integer I, okay, and the reference points to I itself. Okay. The idea is that while you're pointing the while you're making sure a pointer points to the variable I, you have to use the um, address of it. Okay, so you're passing the address of it so that the pointer PTR stores it. Okay, and this is of integer I, so the data type of pointer is also integer. Okay, similarly for the reference, you use the ampersand here to essentially say that ref here is just an alias for I. Okay. And then let's say you try to change ref or PTR. Okay. Either by directly changing ref or directly or you dereferencing PTR first and then changing the value. You see that I changes in both cases. Okay. Now let's suppose here this is what we have been seeing, right? There is a variable and two things are pointing to it in a way, either by an alias or having actual pointer pointing to it. Okay. And changing either of these changes the actual original value. Okay. But let's suppose we consider constant pointers and constant references. So the way to define this is you add the const keywords, okay, in front of all the previous instantiations. Okay. So integer pointer, const pointer, like const integer pointer, const pointer. So take pass the address. The difference now is that this const pointer and const references themselves cannot change those values, whatever they're pointing to or whatever they're referencing. Okay. So it actually throws error, right? There is a way to temporarily make your variable not const and then change the value. Okay. And that is using const casting. Remember, const casting does not make the variable const. It actually removes the constness temporarily. Okay. So that you can change the value. Okay. Right. So this is the syntax for the reference part. And so this is a C style way of C++ style way of doing things. And if you want to do the C style way, you can cast it as integer reference like this. Okay. Pretty similar. Here you use const casting to pass the template as a integer reference. Here you just use the brackets, right? And here you're passing the variable. Here you're just using the variable directly. Very similar to that. You cast it as integer pointer here and dereference it. Here you're dereferencing after casting to integer pointer. Pretty similar syntax in C++ and C, but they essentially do the same thing. Okay. So either use const casting or use typecasting here to change the variable like temporarily so that you can write the values, okay, uh, to the references or to the pointer. Essentially, you're doing the change so that the original value I also gets changed, right? Now, here the important thing to remember is the variables themselves, which are referring to I, are const, okay? Hence, you need all this way of changing the constness temporarily and changing the value. Okay. But if I itself was constant, you still, even if you temporarily remove the constness in the variable, you cannot change the original value because it is not it is not just integer, plain integer. Okay. Now that if that itself becomes const, you cannot do any of this anyway. So the idea is that const variables should not change, still preserves. Okay. That idea is still respected. Okay. All right. So if that is the case, using const casting will not change the value even if you try to change it. Okay. There is sort of a check inside defined in the class, apparently. So yeah, you can sort of safely try to const cast. If the value changes, well and good. Otherwise, if it is const from the beginning, then it won't. Okay. Then we saw, oh, okay, I should maybe should start with typecasting itself, but yeah. Then we saw about typecasting. We have integers, floats, and doubles, right? And printing this, you see the value that gets printed. Important thing to note, they are of different sizes. So your computer itself will use different bits, different number of bits to store the same value. So it uses 32 bits for integer and float, okay? And for double, it uses 64 bits, right? Now, when you're converting an integer to a double, okay, you're sort of promoting it, right, to a higher bit value. In general cases where whatever the range usually I has, they all can be represented in double. So there is sort of an implicit cast from integer to double, and that's what you see here. You can do it explicitly, okay? So that you can just use this C-style way of explicit casting to achieve the same thing, right? But if you go from double to integer, okay, you have to do an explicit cast because here you're actually changing the data type from higher to lower. So there will be a loss of information. Furthermore, you're sort of, if you think about it, double have decimals, right? And integers have just the integral part. So since you are actually trimming off data, there is a loss. There is a loss in data essentially, right? So in these cases, the compiler won't just plain old typecast it for you, okay, with implicitly. You have to explicitly do that, right? And this is the order in which promotion you can think like from left to right. The higher the preferences. Okay. Also, you can use standard precision to print as many digits you like. Okay. Then you can actually check, let's say, certain number when represented in float and certain number represented in double. They will differ after certain digits. Okay. But you can be assured that the double, since it has more bits, will represent that number more accurately than float. Okay. Then coming to the next example, right? So here we take integer I, okay? We take a pointer p pointing to I itself, and then we make an array A of 10 values, all of them being integer, okay? Next, we make a double variable, another q pointer, which is now pointing to D, okay? And a void pointer R, right? Next, if we try to write key equals to P, so where you're here essentially trying to write address. P also is a pointer and Q is a pointer, right? Each of them contain addresses, and the storage size itself of Q and P is exactly the same. It is, can anybody tell me what is the size of Q and P?
P 4 bytes, Q 8 bytes.
Sorry, repeat.
P is of 4 bytes, Q is of 8 bytes.
Oh no, that's not exactly true. Both of them are of 8 bytes. Okay, so why I say that is P is a pointer, yes, but the variable itself that stores the address is always of size underscore T. Okay, which is the largest representable integer, unsigned integer in your system. Okay, and for me here it will be 8 bytes. The integer qualification here or double qualification here for this pointer. Okay, here if you see, if I compare Q and P, so the changes in the name P and Q. Okay, both of them are pointers, and but the only difference is that the data type, integer or double. Okay, the integer or the double here does not refer to the value that the pointer itself stores. Okay, always remember this data type always tells you what is the data type it is pointing to actually. Meaning, if P is pointing to something, here it has to be integer. So hence, if you try to give it an address of some variable, you have to give it of that of integer. Technically, you can give it anything, but it expects that to be integer. Meaning, P itself is of 8 bytes. It stores a some number, okay, which is some integral number, which is an address, okay, of 8 bytes. And when it actually points to whatever in that address has the integer I. Okay, very similar to that. Q also is pointing to the double 7.5. Okay, and the address of D is what Q has itself. Okay, that Q itself is the variable which has the address. Okay, and the size of this variable is always size underscore T. Okay, or here in our case it will be 8 bytes. The qualification double just tells you that whatever data type it is referring to, okay, will always be double, is what the qualification says. That's all. Yes, you can always play around with the typecasting as we will see now, but this is the essential idea. Now, because the actual variable these pointers are pointing to are different, okay, changing one from the other like this is not allowed implicitly, okay, right? But as such, thinking about it, if you store this Q and P in some variable A and B, where both of them are integers, let's say they're long integer and long unsigned long integers, okay, then you can actually switch A and B again, okay, because you're just playing around with integers now, okay. I hope this is clear, okay. But yeah, please do attempt try to attempt these questions, because that's how you'll actually clear your concepts. But yes, that's good. Yeah. Moving on, if you try to print Q, you'll see the address that is actually stored inside Q. And when you dereference Q, you're actually referring to the value stored in that address. So you access the address, then try to access the value at that address. That is what dereferencing is. Okay. That should print 7.5. Okay. Similarly, if you try to print P and dereference it, it will print the address of I and the value 3. Okay. That's what we see also, right? Now, for example, what you want to do is explicitly write the pointer. It's absolutely fine. There is no actual loss here because Q and P have the exact same storage capacity, which is of 8 bytes. So you can technically write this hex number, like this hex number is stored in P, this hex number is stored in Q. So we are writing this value where this current value currently is. So this value is currently in Q. We are overwriting this value there, which comes from P. Okay. And these two values take exactly the same space. Okay. 64-bit integer. But to do that, you cannot do this explicitly. Implicitly. You have to do it explicitly. Okay. Because Q expects a double pointer, you can actually just tell that whatever P has address, just consider that the value that it contains is not integer anymore, okay, which is actually the number 3. But consider those, and let's say 3 is of this representation, okay. Obviously, this is not 3, but let's assume, or whatever original value it was in integer, but in binary, it looks something like this, in some form of zeros and ones. So what you're telling it is, whatever the value it actually was containing in this address, right? In this starting address and whatever plus 64 bits. Okay. So this is a starting address where this will be the value. Okay. So at this address, you can think like 0 is at this address, and whatever this end 0 is will be some 64-bit addition to this address. Okay. Now from this starting to this end, whatever be the sequence of zeros and ones, okay, they will be considered as a double. So the same sequence of integer. Okay, now here you have to be careful also. Integer would have had just values till 32 bits, right? But now you're saying I'm converting to a double, so it will actually go beyond. Okay, this is also very important to understand. It won't just look at the first 32 bits, it will also look at the next 32 bits, because you told you told here Q here that consider the address coming from P as a double. So it will start at the same address as P, but it will consider 64 bits, okay, and treat that new number, okay, sequence of bits as floating point number and convert it to a decimal number. That's what we saw. It came up with some uh, other value, okay, which is not 3, of course, but that is the idea. Okay, then if you try to print these Qs, you'll see the value is similar to P. Not the data reference value, but at least the address. Okay, any questions so far? All right, moving on. You can do a very pretty similar thing in this case also, where you are saying to P that, hey, you will be getting an integer pointer. I'm just plain old typecasting Q to just be treated as an integer pointer. Now Q actually is a double pointer, okay, storing the value 7.5, sorry, pointing to D with some address, okay, it's storing some address of D, where pointing to D, okay, and that has the value 7.5. Here the interesting thing is that when the opposite thing happens, the actual sequence that Q was pointing to, okay, will be of 64 bits, because double is of 64 bits, right? And when you say P that you treat that those starting address as an integer now, it will not consider the whole 64 bits. It will take the first 32 bits, okay, whatever zeros and ones it sequence it gets, right? Treat that in the 2's complement for notation, okay, right? It's essentially that, right? So you have a sequence of 32 bits. You want to treat it as integer, it has a certain rule. You want to treat it as a floating point number, it has a different rule. You'll just apply those rules. Okay. First of all, in the previous case, it applied the integer, like it applied the floating point rule. Now it will apply the 2's complement, or the way integers are represented in computers. So it will take the first 32 bits, convert that to integer, and then when you do a dereference of P, that's what you will read. Okay. So technically, you can actually print P0 and P1 here. Okay, because D actually stores 7.5, so it has 64 bits, right? So the actual memory is realistically allocated for 64 bits. So there is nothing wrong you're doing by accessing those 64 bits, or in chunks of 32 bits, 32 bits. Okay, that is allowed to you. I mean, it does not mean much when you represent 7.5 in 64-bit of bits sequence of zeros and ones, and then chop it and then split it in between 32 bits and 32 bits, and then read them off individually. I don't know why would anybody want to do that, but then again, you can do it. So you can print P0 and P1 as in square bracket. Okay. This is an exercise you guys can try. In the same example, when you dereference P, it only reads the first value, first 4 bytes or 32 bits. So that's what it will do. You can actually try doing this. This will not throw any set points. All right. Okay. Moving on. Any questions so far? All right. So now we consider the void pointer R. Here, when you try to write any pointer to void pointer, it implicitly casts it, and compiler does not um, throw any error or anything. The reason being, it's okay to it's sort of a promotion actually. So if you think about this case, there is nothing wrong with throwing away the data. here in this, what I mean by that is, if you're saying that whatever the address is actually pointing to, let's say Q, it's pointing to D, and that has a of data type double. Okay. Compiler is fine if you don't remember that anymore. Okay. The pointer does not want to remember that, that's absolutely okay. But let's say, uh, okay, this is this implicit way of doing. You can also do it explicitly. There's nothing wrong with that. But if you are storing a pointer R, which was void type, okay, into P or Q, either way. So you're essentially saying that now you want to treat it as integer or double. Okay. Now that in itself is actually a source of error. So by itself, that is not allowed implicitly. So you have to do it explicitly so that you actually know what you are doing, if you think about it. So with this line, you're explicitly saying that, yes, I know it is a void pointer, but I want to treat it as an integer pointer. Meaning, whatever the sequence of zeros and ones, whatever the address it has, okay, and that address has some sequence of zeros and ones, I want to treat the first 4 bytes, okay, take that and then treat them subsequently as integers. That's it. And remember, in all these cases, while you are transferring addresses from one to the other and treating the same location and its subsequent 32 bits or 64 bits as any kind of number, double, float, integer, or anything, there is no out of bounds check. Okay, implicitly, there is no check. Compiler does not check all those things. You ask it to read something, it will just read it off. Okay, and if you start writing data to it, also it will probably do it. Okay, and now if those memory regions, okay, are not supposed to be owned by your program, that's when you get seg faults. Okay, so segmentation faults or out of bound accesses. Okay. Okay. So hence remember that only access the values that is allocated by you. So here the only allocation we have done is the integer I, okay, and the uh, uh, C style array and the double variable. That's it. We're not allocated anything else. I mean, there are variables P and Q just and R also, which store addresses, but then in itself they don't point to any variable as such, if you think about it. Okay. I mean, they themselves not storing any other data. They just store addresses. You can go beyond. You can also access the address of this pointer itself and then play around with it. Again, that is also fine. But yeah, something to be aware of. Okay. Right. So moving on. So we can implicitly cast from higher, like some kind of integer or double or any other pointer to the void pointer. Okay, so the reverse is not possible implicitly. You can do it explicitly. So doing that, you can now access those values in different form, right? This is a nice way where you can actually think about type erasing. So this way of typecasting treats all whatever pointer it gets as a void pointer, okay, passes it around, and then at appropriate time, it can just you can typecast the void pointer to whatever required. Given that's the correct way of doing the writing the code, let's say for that region. Okay, so something to take note of. Here, this is essentially type erasure. Okay, this is how it works. But essentially, okay, by passing it as void pointers. Hence, you'll see in a lot of libraries, this is how pointers are passed, because you can just pass everything as void pointer and let the library decide which data type it wants to cast it into and read it off. Which also you mentioned depending on the library you're calling. Okay. Right. This also we saw. So this is C style array. So the ith location you can access by the square brackets and write it as I. Okay. Furthermore, you can do a pointer arithmetic. So you can take the first uh, the variable A itself, which has the address, and when you add I to it, it moves by certain numbers. So it will be plus in technically the address now it is actually referring to is not just A, let's say it was um, 10,000, okay, and plus 0. No, that's not how it works. It is actually 10,000 plus I times the data type of A. So A is here, if you go back again, integer. So 4 bytes. Okay. So whatever 4 bytes corresponds to, that gets multiplied with I and then gets added to 10,000 or whatever the number is in hex. Okay. And then when you dereference it, you get the actual value there in that location, and then you write to it. This is just a shorthand representation, the bracket operator here, or shorthand representation of this thing. Okay, that's all. Yeah, correct. Okay. Also, you can do it this way. You can store the address of A into P because P is a integer, right? Integer pointer, and you can dereference P to print all the values of A. Right? You cannot do the opposite. Remember that, because when A is allocated, the only pointer pointing to those values, 10 values that we initially saw here, is the variable A. That's the starting address. And no other value is actually pointing to it. So if you overwrite whatever with A with some other value, those become dangling. Like that section of memory just becomes dangled. It's not being freed, and your program has lost that memory. Okay. So to avoid those things, this certain line here does not work. You cannot store overwrite, I should say, A with this another address, even if they're both of the same data type. Normally, you are allowed to do that. If they are of same data type, you can just overwrite it. Okay. But in this case, yeah, it's not allowed. Right. Okay. Moving on.
So, sir, in general, we can assume that we should not do downcasting, but can do upcasting.
You can, yeah, I mean, in general, there is nothing stopping you from doing casting. If you know what you're doing, you can cast anything to anything, technically. But implicit casting, wherever possible, it allows you when it also, the compiler says that, okay, you're not actually losing much, so it's okay. I'll allow the implicit casting. But as a good practice, I would say always do the explicit casting, because then you're sure what you're doing is actually mentioned there. It helps in catching bugs. That is one thing. Second thing is the intention is clear. So whenever you write good programs or good code, the main thing is the intention should be clear. So I'll show you some other ways of typecasting, but the essential idea is that you either do the C way or the C++ way. In either case, the intention is the important thing. Yeah, there are rules you can think of it like, okay, should I go with downcasting or upcasting or other things? But in general, I would say explicitly mentioning things is the best way to go. I wouldn't say it's a bad habit to use implicit casting, but then again, it's okay. Some cases it says fine. Yeah. Okay.
So suppose if we do downcasting from so suppose I want to write to a 8 byte of length, but I am accessing 4 bytes from it only. Then
Mhm.
what happens to those leftover 4 bytes?
Yeah,
Because so it's kind of memory loss, right? Because
um,
I am consuming those memory, but I am not using it.
right. So let's say you have a double like of 8 bytes, and you are uh, let's say that is double. The variable is d, and you have an integer, or let's say float itself, some f. Okay, you are writing f equal to d, right? And you are downcasting, right? Is that representative of your example?
Yeah.
Okay, so d itself also exists, right? We have not erased that. So that data itself is there. It just so happens that whatever data f had, of 4 bytes, that gets overwritten. That's all. So let's say F had 2.1 and D has, again, let's say 7.5. So now 7.5, which was represented in 64 bits, is just now being represented in 32 bits. Now, will there be a loss if a real number gets represented in 64 bits to 32 bits? That absolutely depends on the representation rule. In our case, for 7.5 being too small, it is okay. 7.5 can be easily represented exactly in 64, both 64 bits and 32-bit floating point numbers. So your F will now have 7.5 exactly. Okay, so it's just that D had 7.5 represented in 64 bits. So the arrangement of zeros and ones looks a little different than the arrangement of zeros and ones in F. But if one reads it off, when I say read it off, means you read off the 64-bit value, 64 bits from one location, which is the D, and convert to decimal, you get the value 7.5. And when you do the same for F, you also get 7.5. It just so happens that the value which was 2.1 earlier represented in 32 bits, okay, zeros and ones, which was there earlier in F, just gets destroyed. That's you just lose that value. But when you're typecasting from a certain value to another, the original value is still there. Like we did not touch D. Okay. So that value still exists. You only lose the value you're overwriting. Okay. I think this example is clear. If I may, I can, let's say I take very large number. It is so possible that the number is so large that 64 bits are actually required to represent that value in floating point numbers. It just so happens that float might not be able to represent it accurately. Okay. So in that case, there are rules. You can typecast it, but it's essentially like you can think of it like there's a range of what floats can represent. There's a range in what doubles can represent. So when you downcast, you will try to bring it closest to the actual float 32-bit representation it can. It's essentially a best effort basis, but yeah, that's it. Okay. But for small values, you won't notice this difference, like 7.5. Okay, is that clear?
Yes, kind of. Also,
Okay,
let's
sure.
suppose we take up the memory from heap.
Mhm.
Let's say in so let's say a variable taking memory in heap is a type of double.
Mhm.
So I'm looking the answers in terms of memory perspective. Why would I cast it to, let's say, float?
Oh, yeah. Nothing. So, um,
Yeah, I am not being
yeah,
stopped from doing so, but
yeah,
I
right.
am not able to visualize why would someone do so by reserving
So
memory for 8 bytes but using only 4 bytes.
4 bytes only. Yeah. Sometimes you can think of it. Okay, I'll give you a modern example. So let's say there was a file, okay, or an external library. Okay, that library gives you some output. Okay, and it just so happens that it will always give you the most precise it can. As in, let's say the most common is double. So it will always give you double values. Okay, be it an external library or an external file, whatever it is. That is, you don't have control over that. Let's say, okay, what you have control is your own code, which what it does is it just so happens that it is going to compute some more output. Okay, right, where the input comes from externally. That's all we care about. For now, how it comes up, it can be library or it can be file. Now, let's say you have a file, your own code, right? What its intention to do is it will calculate certain values and give you some output. Okay. It just so happens that whatever the function you are doing, okay, it is very costly. Let's say. Then, if you think about it, working with values which are double is more expensive than working with values which are float. Okay. And it just so happens that, let's say, the output that you get, you're okay with the precision that float gives you. Let's just assume. So in that case, what you can then do is, what are the input you're getting from the file or the external library, you can just typecast it to float. perform your computation, which will be fast because they're all in 32-bit representation. Okay, it will be faster than double, right? Get your output, and you are ensure that since output itself is accurate enough for you, okay, for your example, then pass it on to some other library or write it or something else. Okay. In examples like this, again, I must tell you, this is also very common these days because of a lot of applications are trying to move into lower precision hardware and still uh, preserving accuracy. There are more details to it, but you can think like this is sort of the idea that they do. You can also try to store the same thing float as a double, okay, and then pass it on. You can also have a choice to do that. But as such, you have already, because I've already converted to float already, converted to double itself also does not make sense. But then again, let's say some other library always takes double. You can also do that. But it so happens that, let's say, whatever output you are getting is good enough for you in terms of lower precision. Okay. So in that case, you can do this. Plus, there's added benefit that because you are dealing with low precision values, you save on speed. Okay? You actually get more speed up.
So it's basically boils down to the kind of application we are developing. So
Exactly.
it may
On
happen
this.
the developer may write a general library, but
Yeah,
it's how you use in your application that matters.
exactly. Yeah,
Okay,
exactly.
fine. Yeah,
Yeah,
thank you.
yeah. It is very application dependent. A lot of scientific applications require double precision. So they again deal with it, but there are ways you can get around this. So there are a lot of research you can, some parts in my research also I do something like this, where you can actually recover, uh, like you can deal with low precision in expensive regions and recover the same accuracy as double. Okay. So there are mixed precision strategies being developed, which is also a very interesting area of research. So again, if people are interested, you can look into it. Okay. Right. Yeah. Okay. So let's take another example from today. So we'll take the basis will be the topic of typecasting itself, but let's take more examples to understand this. Oh, my bad. Sorry, I was doing. So we'll include as usual. We need to print stuff. So I have stream. I'll make a class. Let's call it A. It has public members. Integer I 7. Let's say another class B, which will have, let's say, public members. Now it has double B, which let's say is 0.2. Now let's call the main function. Let's instantiate an object A. Okay, this is perfectly valid. I'm using the class as the data type, and the variable as for the name of the object is A, and it will use the default constructor. So this is perfectly valid. It's not take any input or anything. It just instantiates the object. Okay. So now A has a member I, which has the value 7. That's it. Okay. Very similar to that. I can define D, where the variable D is part of the object B now. Okay. And has the value 0.2. That's it. Plain and simple. Okay. Now let's say I define pointers. Okay. Equals to address of A. Okay. Now also very similar to that. As address of B. This is valid because A is of data type capital A. That is a class CS, but it's what's its data type? It's capital A. So if I take the address, so the pointer which naturally will store it without any typecasting business or anything, and obviously compiler not throwing any error, has to be a pointer of data type of that class, that same name, right? It's a pointer, yes. Its name is P here, but what will the data type be? It has to be capital M. Okay. Think of think of previously when we took examples, it was with inbuilt data types, integer, float, double, and so on and so forth. Now just replace those names with some other class name, like some custom defined data type. That's it. Pretty much all the things that you see before sort of hold. Okay. I mean, again, to certain extent, yes, but that's sort of the idea while defining from perspective, at least pointers. Okay. So instead of just using integer, now we are using the data type class name to define pointers, right? Okay. I must say there are some differences between inbuilt data types and then using custom defined data types like this. Now, this is what we're going to see now. So we define P of a pointer, Q of P pointer, capital P. Okay. So this is fine. This is allowed. Let's run this actually. So yeah, runs fine. On good. Now let's say we do it this way. So what we're trying to do is write the object B into A. Okay. So what do you guys think? Is this allowed? Okay, not okay?
Not okay,
Okay, why is that?
because they are of different classes and the classes are of different types,
Right,
kind of.
right. By definition itself, when you have different classes, they are of different data types. Even if they are user defined, yes, but one can consider them to be different data types. And
Yeah.
and there is no inbuilt prescription to convert or implicitly convert one data type to another. For integers, it exists. For double, float, because these are inbuilt data types, okay, there is a rule which relates decimals to binary in all these formats, right? And one to the other. So integers are represented using 2's complement. Floating point representation is done using IEEE 754. So there is a standard to how all these are defined. Okay. And how one data type relates to the other. One can actually think about it. But when you have generic data types like A and B, there is no rule here, right? Okay. So something like this will actually throw an error. That's what we see here. Not to say that it can't be done. Again, there are ways it can be done, but implicitly, no, that's not allowed. Okay. Right. Very similar to that. Also, not allowed. Okay. I'll just comment this so that let's see. This is also my error. All right. So comment this too. Yeah. Now, what about I try to write A equals to B. Before we saw that we're trying to do it implicitly, right? What about we do it this way? I know the data type A is capital A. What about I just cast it into A and then write it? I mean, seems fine. It worked before. Should work now too, right? What do you guys think?
Yes.
Should work? Okay. Recall what I just said before. It won't work. The reason being, even if we say that we want to convert, there should be some mechanism to it to convert, right? By that I mean, when we were converting, okay, I'll maybe refer to this. When we were converting a double to and rewriting it as an integer to I, it just means that you take the memory location. Okay. So now D itself had 64 bits, right? Okay, let's think of it like this. Not just integer. Okay, fine. Let's continue this example. D had 64 bits and you're trying to convert it into integer. So those 64 bits now will be looked into as 32 bits and this read it off as an integer. So there is a rule there, as in there is a standard which can be followed to convert from one to another. Um, right? Oh, sorry about that. Yeah, right. But what's the rule that converts this generic class B to A? Nothing. There is no rule. So as such, even if you try to convert B to A, okay? So B is of data type B and A is of data type A. What is the conversion rule there? That doesn't exist because these are custom data types. We just made it ourselves. But for inbuilt data types like integer, float, and so forth, there exists a rule as to how to actually represent those bits. In memory itself, B also has a location. In memory itself, A has a location. Yes. And there are some bits representing this class. Okay. Remember, your integer I is a member. Yes. Which will take 4 bytes. Yes, absolutely. But is the starting address of I the same starting address of A? No, it's not. There is a way in which there will be some bits used to define A. Nobody knows what's the representation is. It depends on the compiler. It depends on your OS. Okay. But there is a address which starts for this class. That much is sure. Okay. And there is an endpoint to it from certain address to another address. In somewhere between that, there is an integer I. That's all. Now, how this complete representation of zeros and ones for this A looks like, it completely depends on the implementation by your compiler. Okay, it will vary so much from compiler to compiler, from architecture to architecture, that there is no generic rule to convert this representation to this representation of zeros and ones in memory. So, and the standard itself cannot actually also enforce this, because you can have very different classes. How does your compiler know to convert from this class to this class? It's not possible. So the standard does not even define it. And hence it does not allow you to do certain things like this. Okay. I hope you appreciate the idea of typecasting. Typecasting is not just, it just not, does not just mean that you had a variable and you just treat it as a different variable. There should be a rule existing, okay, to actually treat that existing variable to a new variable, which does for double input variables like integer, double, and so on and so forth. Since it exists, you can freely do all this typecasting and other examples that we saw, but not so much for classes. Okay, I hope that's clear. Right? Just to check again. Error, right? Very similar to that. If I uh, my bad. If I do the opposite way, where I'm typecasting A to B, okay, I think you guys can expect what should happen now. Again, that also throws an error. It goes both ways. There is no rule that converts B to A. Again, there is no rule that converts A to B. This also throws an error. So hence you cannot typecast classes. Okay, right? Very similar. But what about pointers? Remember, pointers themselves just store addresses. So they don't have anything to do with data types itself as such. So do you guys think this will work?
Yes.
Okay.
No,
Ideally,
it's like kind of
yeah,
converting two different data types to one another. It's kind
right.
of, yeah,
Uh-huh.
star
Yeah,
int. Maybe if we say p is pointing to an integer or q a double, then you cannot cast to double to int star, double star to int star kind of thing.
repeat the last line. If you're, let's say you
So
point to this,
if there is no classes and p is pointing to an integer and q is pointing, so p is a pointer to integer and q is pointer to a double. So here q equals to p, we are converting double star to int star.
right?
So that is not possible implicitly.
Implicitly, right? Yes,
So same here, we cannot do with these classes also,
that's correct.
or we
Yes,
can
that's
say
the
there is
correct
no
answer.
mechanism.
There's no mechanism. So it's like ideally, it compiler, let's say it allows it to. Okay, um, this is absolutely possible as such. Like it's exact the same logic as before. You can store whatever the value is there inside P and Q in one or the other. So they're both unsigned long integers, as in 8-byte integers. Okay, they can be interchanged. It just so happens that the reason a compiler does not allow it is it does not allow it as implicitly. Okay, that's the only reason. Because it sees that these are different data type pointers, as in the pointers are referring to different data types. So to protect the uh, user here or the coder, it just does not allow it implicitly. That's all. There is no reason that you cannot do this, but you just have to do it implicitly. Okay, that's all. But yes, that's the correct answer. Okay, let me run that also to check. Yes, that's correct. Error. Okay, similarly with Q equals to P, you get the same error, which I'll just confirm it again. Oh, sorry. And this, yeah, it also shows the same thing. So that's good. Right? Confirmed. Same arguments. The reason that it does not allow is not because that it cannot be done. Okay, like which was the case here. Here, even if you want to do it, it is not possible. That's the argument you can go with if you want to make an analysis. Here it is possible, yes, but just not implicitly possible. You can do it, but you have to be more explicit about it. Okay. Now, what we can then do is make P equal to Q, but Q is of what? Data type B, and P is of data type A. So we'll typecast Q into A. Use typecast. Okay. Now, let's say you run this. All good. Okay. This essentially just means that whatever address you had, you want to convert to P. This is what we were trying to do here. Just you have to be more explicit about it. You have to typecast. Okay. Right. Similarly, you can do the reverse way. Compile it. Also, there is all right. But I think there will be a question here. What does this even mean? Okay. So originally, you were not able to convert one to the other anyway, right? You tried converting them, like overwriting, didn't work. You tried converting them, also did not work. Pointers themselves also, when you think about it, it is pointing, yes, but when you dereference it, let's say you want to dereference P here. Let's take this example. If I dereference P, I can access the object A, right? Everybody will agree to that? Because I'm storing the address of A. So if I dereference P, I'll get the object A, right? Very similar to that. If I dereference Q, I'll get the object B, right? And I can access its methods and all those members and everything through the pointer, right? But if I do this, okay, the original pointer was Q, okay. But now if I treat it as A and try to dereference P, what does that mean? It will if somebody want to take a try, what will that try to do? What's going to happen? Think of the earlier analogy I gave, where the representation of any class is a sequence of bits in the memory. Okay. There is a sequence for A, there is a sequence for B. Okay. And they need not match. Very likely they won't match. Okay. Now when you take the address of Q, okay, which was actually of for B, um, the sequence of B's for representing the object B, let's say it was the sequence starting with 0, 1, and so on and so forth. That will look completely different for A, right? By doing this, you are just telling your compiler while let's say you want to dereference P, you have to do like star P, okay? And let's say access P is of data type A, right? So you can access I. So you can't do dot since it's a pointer, you have to use the arrow operator, do I. Do you think this will print 7? It won't. You can access it, try to do something like this, but what it will give you is completely different thing than what you expected. Reason being, the address starting at Q actually does not store any object of A, it stores B. And the sequence of zeros and ones that actually is there in memory of B refers to the class, which is B. It has nothing to do with A. Okay? Meaning, what I'm trying to get at is, you can absolutely do something like this. Okay? But it's not useful. Like, again, one. Second thing is, you cannot use any of the methods that you already have. Okay? I hope you understand why you cannot do any of this. I mean, maybe it will allow you to do it, but again, it depends how much memory was allocated for each of this, for class A, for class B. Okay, so if let's say class A has um, class B actually allocates less memory, okay, or it's just so it's not sufficient for A to access, you might actually go out of bounds. That's possible. You might run into set fault, or you might actually print something, but it will be some garbage value. Let's try it. You can try printing this, but there's no guarantee that it will print anything. I mean, it might actually run into set faults, but let's see. I can test it for you. So let's go ahead. But it's most likely, definitely, well, not definitely, but again, most likely won't print 7. Okay, let's go with that. Right. Yeah, again, it's an invalid pointer. So yeah.
So either it should be star p dot I or p reference operator to I,
Um, yeah,
because p
that's
is a
correct.
pointer to class A.
First pointer. Yeah, I can just do this or the other one. Yes. Yeah, it printed some value. Now it went to that memory location. I guess it was it okay. Sometimes programs do not actually throw errors if even if it's seg fault. So be careful. It is possible that the region it is actually accessing it may not be accessible to this current program, but then again, nonetheless, it went ahead, okay, treated the memory location of B, which we allocated, read off the value I as an integer and just printed something. Okay, definitely not 7, but some number. Okay. Yes, that's correct. You could do it this way also. It's yeah, thanks for that. Yeah, because we dereferenced it already, so we can use the dot operator. That's correct. Yes. Sorry, my bad. Why is it
Now
showing two
we need
times?
bracket.
Need the bracket. Okay. It's getting confused. Which to operate first? Ah, yeah, that's why it's twice. Yeah, okay. Right. So let's say we do it this way. So it should print twice. Yeah, it prints the same value at least. So At least you know that whatever syntax you're using is correct. That's all. That's all you can say about it. Right. Okay. Oh, another thing. We should actually do this. Yeah, because we're actually going back and forth twice. So let's do it once. Yeah. We overwrote the pointer as P, and this happened. So if we do Q, so then what we need to do is change to Q. Yeah, everything should work. Right. I'll respect it. Okay. Oh, my bad. Q does not have I, it has P. Now it should work. So it printed some value again. Okay. Definitely not 0.2, as you can see, right? Okay. Right. Okay. Any questions?
Sir, will the friend function will work here or derived classes?
Um, Similar issues. So you can make friend functions. So, okay. Friend functions, let's say for this class and so on and so forth, you're accessing the actual objects thing, whatever you saw before. Let's say I make a derived class of B, then reference that object of B and all that. Whatever you did before will be absolutely fine. All that is okay. But if you typecast it this way, then everything is up in the air. You can access all these methods and all, friend function and all that. But let's say the region, the total memory size taken up by class A will be different than whatever B takes, right? So it is very much possible if you try to access some memory, you might go out of bounds. That is one problem. The second thing is, let's say it does not, it is fine. Whatever access memory access you're doing is within the program, so it is all fine, accessible. You can access the friend function. You can do the derived class. Its members. Let's say you can access all those. What it will print will be very much similar to what we saw now. With some very garbage or large number, something. But yes, that will work. Yes, as in within the limits of, let's say it is in the memory is allocated and you're not doing too much out of bounds access and so on and so forth. Then yes, it will work. Yeah, because nothing stops you from um, casting it this way. Just that whatever sequence it was treating B as, will it will treat the same sequence sort of for this object A. As in the class A was defined with some uh, blueprint in mind. Okay, just so happens that the starting address was for this guy, but it will take that starting address and start treating it as B. Okay, that's the only thing, the takeaway here, using typecasting of pointers. Okay, right? Implicitly,
Okay,
hence,
okay, sir.
yeah, yeah. Implicitly, hence, these things are not allowed because, as you can see, this can lead to very weird errors. But yeah, if you are, if you essentially that's the end thing in C and C++. If you know what you're doing, you can use pointers to however you like. That's the idea. But
So,
implicitly, yeah.
can we say that there is no meaning of typecasting for user-defined data types?
In general, yes, I would say so. You can actually
Because
convert everything to void pointer, but
Mhm.
let's say there is a library which has some definition of B, right? And let's say it expects uh, class B in some other library. It's possible. Again, it depends on compiler and all those things. But let's say there is some rule which defines the whole thing. You can pass everything as void pointers and then typecast it back to B, and then it will work. Another thing you can do is maybe you can use the same definition and move around pointers, let's say from one file to the other. One file, when I say, let's say it is not just single file. Okay, you have multiple. It's a huge project, multiple files. In some place, we are using class B definition, defined a object of it, casted into void pointer, moved it around everywhere so that I don't have to have the data type B point B star. So if you remember, whenever you try to pass around any pointer, you need the data type there, right? So what I can then do is cast it into void pointer. So then I don't need to, I can do a type erasure, right? So then I can move that void pointer across many files. Finally, when it gets to the file where it has access to, let's say, this class definition, I just convert it back and then reuse it. It will absolutely work. Okay, I hope that example is a little clear. I'll explain it again if that's not clear.
That's okay.
It's okay. Yeah.
And for the rule you mentioned, what are those rules? Are those some methods inside those classes, or we need to write special constructor for that?
For what?
Suppose at line 24, we are
Mm.
unable to do a casting from A to class B type.
Mm.
So in class B, do we need to write a constructor or method
This
to make
is,
this statement work?
I did not.
Line 24.
Yeah, there's a mistake there. Sorry for that. Yeah. Yeah. So rule as such. Okay, think of it this way. Um, that would require probably how the compiler itself represents the class inside memory, right? There is no definite, um, how to put it? There's no rule that it's which says no, this is integer. You have to read bits of 32 bits, okay, of integer and convert it to decimal in this format. There is no rules as such which represents class B into some known thing as such. I mean, say this is a class, yes, and yes, of course, it will be represented in binary, in zeros and ones, in some memory. But what do you convert it to? What is the class in decimal? Or what is the data type output, which prints that this is class? There is nothing like that. I hope you get my point. I mean, there is one can, I mean, that is the starting point as to if you want to represent some classes in some known print, okay, one can actually maybe write something like that, but as such, the standard does not define anything like that, is what I'm getting at. So if I print a number in decimals, let's in binary, convert it into decimal, that is what it will print when I print all these values, right? The actual location of P of I is some garbage, but it treats that 4 bytes into a decimal, like as an integer, converts into decimal, and then that's what I get in the display when I print. But the same thing, if I think about this guy, what does that mean? For class B, class B takes some bytes, let's say, in memory. When I convert it into some new, not decimal, but some decimal equivalent, what will it look like? There is the standard does not define it. One can maybe define it, but then that's like changing the how the language itself works, I feel. Okay. Okay, is that clear?
Okay.
Okay. Right. Very similar to that, but let's take more example. Essentially, we're building on top of each example before. So let's look at class A. method is public, and again, integer I is, yeah, let's not worry. No need to even define in the value for it. That's fine, exactly. Yeah, now this time, yeah, we'll make this as a derived class. Pretty similar to before, but this time instead of A and B, I mean, as in two different classes, we'll make one as a derived of the other. Things get a little interesting here. We'll define the object A, okay, as before. Define object B. We'll make pointers of address of A. The pointers, like that. G, it's the address of B. Yeah, that's it. Now also I'll define void pointers. So because pointers, so why not? And let's say I make A equals to B. Okay, what do you guys think will happen? Remember, this is also a class, and A is also a class. Like pretty much similar to before, but slight difference. B is now derived class of A. Any guesses? All right. So yeah, let's run it. Oh, it actually did not throw an error. Must be some difference between derived and public. So actually that's actually true. Um, if you are if you think about it, when you derive a class from a base class A, and you're using the you're saying that I'm going to write B into A, right? That is allowed because again, that is the base class. A is the base class. I know, seems a little um, unintuitive, but if you think about it, uh, class B has all the elements of A. Why? By definition, it is a derived because it's a derived class of A. Since A is the base class and B is sort of built on it, right? So yeah, I know it sort of feels like downcasting, and C is sort of allows it. Okay. If you think about it, I mean implicitly, yes. C++ also. B class B has all the members that A has, right? So if I put the object B inside A, right, as a data type, then I should be able to access all the members, which is true because it has the copy of all these members anyway. I hope that idea is sort of clear. Yes, you lose the information that extra information that B might have. You can't access that from A, right? There's a downside, yes. But I hope that this idea is clear why you can do this, right? Again, it's little um, unintuitive. It's not so straightforward to think, because if you try to do the opposite, okay, that actually throws an error, right? It tells you why you cannot. So storing A as B means that you're telling, hey, A, you should be able to access the extra functions that comes with B. As such, it does not have those information, so it cannot do that. Okay. So implicitly, they don't allow it. That's the thing. Okay. So this throws an error. This throws no error. Okay. Right. Okay. Moving on. Let's say I make P equal to Q. Here, like before, we are storing the base class pointer, sorry, the derived class pointer inside the base class pointer. So Q is for B, which is the derived class. P is for A, which is the base class. Okay. So what do you guys think will happen? Very similar idea. Um, Here also it does not throw an error. Explanation is similar as before. It allows the object, so I'm sure pointer should not be in problem, right? Same arguments. The data type of Q is the derived class P. The data type of P is the base class, which is A. So when the pointer gets stored for P, now P can access members of objects, whatever A has, which is possible for B because it's a derived class. Because derived class has all the as a copy of base class, right? It just so happens that it has to forego whatever extra thing it has. That's a downside. But nonetheless, yeah, it can now access a subset of what it was derived from. Okay. I think you guys can guess what will happen now. Essentially, there is a pattern. So yeah, let's confirm it. Yeah, it's an error. Very similar to arguments to this case. Shows an error. Reason being, if you try to dereference it, let's say it implicitly allowed it, and you try to dereference it, P, which is the base class, now has to have extra member functions or variables which are part of the class B, which is a derived class. And those things it will not have any information of, right? So hence, implicitly not allowed. Okay. Now, this, what do you guys think? I just added the void pointer. I think you guys can guess this is also fine. It's very similar to casting any pointer. As long as it's a pointer and you're casting it into void, it doesn't matter. It'll work. It does not matter what kind of pointer you're casting from. Okay. Right. Same for Q. It could be a user-defined data type. It could be inbuilt data type. It does not matter. All the pointers, whichever may be the data type, it can always be casted into void pointer, as in saying take the address of it. That's all. Let's take the opposite example. This has not changed. Okay. So if you try to do this implicitly, again, not allowed. All right. Okay. Any questions? Right. Let's take this same idea and go a little more further. Include a string. A as public number, call it integer data A, okay, class B, public integer data B, right? Define the object for A, define the object for B, okay. Oh yeah, I forgot. We'll make it a derived class. No, I can access A, right? Because it is public, right? So I can access the data from A for A, and let's say I'll store the value 3. B also I can access its own data, right? And let's say I store the value 4, right? Furthermore, because B is a derived class, like this object is of data type class capital B, which is a derived of class derived from the class A. So it itself also has a number A, okay? Because it is public, I can access it outside. Let's store it as 5. Okay. Now I'll make pointers. So start, okay. I'll call it pointer A. Yeah, let's store address of A here, right? Pointer B, pointer, so call it PB to say that this is a pointer to B. Store the address of B. Okay. Now you can read off those values. So you take A, right? Use the arrow operation, access the data A, okay, right? And just print it. This is what we're going to print. Right? Let's do that. Okay, prints 3. That's what we get. So originally A has the value for data A as 3. So if you're using the pointer, dereferencing it and accessing the value gives you the correct value, right? Very similar to that. We'll use B now and say access B. Okay, prints the correct value B of data B, which is 4. Now I can access the data A member also. Let's print that. Which is fine. Okay, all good. That's fine. Now what I can then do is, because what we saw is we can store derived class objects inside the base class, right? So P of A, which actually originally we stored the object of A, right? We can now store B itself. Okay. So while previously A was P of A was pointing to the object A, now P of A will point to the object of B. And B is a derived class. So we can use that to implicitly cast, okay, as a data type for A pointer. Okay, that is allowed because it's a derived class. Okay. I'll print it. Yeah, pretty much print the same thing. Data of A. Data of A. Right. Similar. Print B. Again, printing the last one. Data of A, which is a member of B. Right. All right. As you can see, now because it is pointing to B object, right, which is sorry, the B object is now stored in the base class format. So you'll see certain differences now. Accessing A actually gives you 5, right? And then trying to access B gives you 4. This might look a little confusing, but I hope you sort of understand what we are trying to do here. So let's look at not A, but the B itself. So the address of B is stored in P of B. What we changed here is P of A, right? So P of B should actually not change. If you think about it. So P of B was printing before 4 and 5 for B and A. It is printing 4 and 5 for B and A again. So that did not change. I think you can convince yourself this. So why it did not change? Because we did not change the address of B or anything. We stored the address of B now in A, but the original P of B is still pointing to address of B. Right? Okay. I hope that makes sense. Right? Right. Now,
So it's like 2 pointer pointing to same location.
correct. That's correct. 2 pointers are pointing to the same location, and the data type of B is still intact. So if it was accessing data B or even accessing data A, that has not changed. We still have the same object small b, which has data B as 4, data A as 5. That did not change. We did not, with this operation, we did not change that, right? So these two values that we see here, hence are printing the exactly same thing. Data B was returned to be 4, which is what we see in both the cases. Data A, which is again part of B, has the value 5, which appears in both these cases. This line and the last line. Now, what has changed is P of A. Now, P of A is of data type A. So it has an integer data A. That's it. It does not know anything else. Now, hence, if you try to print data of A, it is printing 5. Why is that? Because it is print now, because B is data A, which is 5, is what is actually now stored in A. It does not store its own data A, right? It is now B of B's data A is the one which is being used to access inside A, like class A. Class A has the data type data A, right? And B, which had derived this member, also has data A. That's fine. But when you store the address of B inside the pointer A, as in the data type class A pointer P of A, okay, this is the this data type. What you're doing is you're saying that I'll be trying to access the only member P of A class A has, which is data of A. But data of A was overwritten for this object B to be 5, right? So hence, when you try to print P of A of data A, right? P of A's data A will print to 5 because that data A, which is it is trying to access now at P of A, is that of P of B. Okay, is that clear? So yeah, that is all for today. Any questions? Yeah, so yeah, that's what I wanted to cover today. Yeah, in the next class, we'll look at more specialized form of typecasting, as in when you're trying to typecast one form to the other, that kind of typecasting has it's sometimes not possible to understand the intention. So we mention explicit forms of castings so that we can cast from one to the other. That's something we'll be seeing next class. And it's essentially the static cast, reinterpret cast, those things. Yeah. So yeah, if you guys have any questions, I'll be here. Feel free to ask. Rest, you guys can feel free to leave. Yeah. Yeah. One more thing, because I'll say example. Because B was able to yeah, okay, that's fine. Uh, we had the data B as the member, which we did use it. Then I don't think it works. Yeah, let's try to access using A the data B. Originally, it did not have access to that, right? And what happens when we try to access it? That's just one example. Yeah, it throws an error. Again, the reason being, um, PFA, right, which is of data type A, does not have any member of like no information about data B as the member. So if you try to access this, yeah, this will throw an error. That's all. Yeah. Okay. Yeah, thank you. Thank you. Hope you guys enjoyed it. Yes. See you guys in the next class. Yes. Thank you. Thank you.